Greetings, welcome to the video 5.51 Prison Isolation Experiment Part 2, Exercise 5.37 introduce an experiment that was conducted with the goal of identifying a treatment that reduces subjects' psychopathic deviant T-scores, where the score measures a person's need for control of his rebellion against control. Or his rebellion against control, excuse me. In exercise 5.37, you evaluated the success of each treatment individually. An alternative analysis involves comparing success of treatments. The relevant ANOVA output is given below. What are the hypotheses? Okay, so before we start this, let's scroll back up and go take a look at 5.37. That would be, there's some valuable information in that problem. Although it was not assigned to us, we still really do need to look at that before we continue with this one. So this gives you a little bit more background into actually what was going on. There were three groups. One group got 4 hours of sensory restriction and a 15-minute therapeutic tape. One got the 4 hours with a emotionally neutral tape on training hunting dogs, and one got the 4 hours and then no tape message that goes along with it. And they want to see what happens to their psychopathic T-score based upon that. All right. So there were 42 subjects total. They were randomly assigned into the treatment groups, and their score was administered before and after each treatment. The distribution of different are pre and post treatments. Scores pre and post are given below, along with some sample statistics. Okay, so the key thing we're really going to need from here is from this table is this: is that what they did is they did what was referred to as a balanced design, which when you're trying to test or compare means, that's really a good idea. You want to make sure that you always balance your samples into each of your respective levels of your factor, okay, or your variable. So in this case, they put 14 in each one of them, which is a really good thing. So that makes their life a lot easier. So make sure you keep that in mind when we come back down here and start actually working this problem. They put 50 in each of them. That's going to be important to know. Okay, all right. So what are the hypotheses? Let's go ahead and get ourselves out a whiteboard here and let's start working on this problem. So what are the null and alternate hypotheses? So the null hypotheses is the mean for treatment 1 is equal to the mean for treatment 2, which is equal to the mean for treatment 3. In other words, out of the three of them, they're all the same. And of course, since we're doing hypotheses, at least one differs. Okay, so at least one of those means is different from the other ones. Okay, so we should come in, of course, when we're conducting a hypothesis test, we should definitely check our assumptions. So we need to check independence. This was done by randomization, so check, we're going to get that. What about normality? If you go back and take a look at the QQ plots on 4.37, even though its sample size are small, not too bad from the normality conditions, so I think we can roll with that. And then the third one was that the variances were equal from each of them. I'll let you go back and take a look at the table. We're just going to roll with that, okay? Because we want to actually conduct this test. Okay, so what are the hypotheses? We've checked our assumptions. What is the conclusion of this test? Use the 5% significance level. Okay, so really all we need to do is come up here and take a look at the corresponding p-value in our table. And we see that the p-value in this case, although not much less than 5%, nonetheless it is less than 5%. So what that tells us is that we would reject the null hypotheses that each of the treatment groups are the same, and that at least one of the treatment groups differs in terms of its ability. Okay, so if in part B you determined that the test statistic conducting pairwise, the test is significant, excuse me, conduct pairwise tests to determine which groups are different from each other. Okay, so you might want to go back and review in the book if you have not spent the time talking about the multiple comparisons and the Bonferroni correction for alpha based upon that. If you're doing multiple comparisons, in other words, you're taking and you're doing t-tests comparing means, pairwise, or excuse me, tests of independence between two means, you can't use the stock out-level alpha of 5%. You have to adjust that because you will find significance eventually whether there was none or not if you start doing all of those pairwise conditions. So the Bonferroni correction says that alpha star is equal to alpha divided by cap k. K is not the number of categories. Don't get that confused. It's kind of a strange thing that your number of groups is a lowercase k. And the way you figure it out, how many groups excuse me, how many, what k is going to be, what number you're going to divide into alpha, is you take k, which is your number of categories. In our case, that's 3. Multiply that times 3 minus 1 and divide that by 2, which ends up coming back equal to 3. 6 divided by 2 is 3. So in our case, for the one we're working with right now, our cap k, not lowercase k, our cap k is going to be equal to 3. So to figure out what our alpha star is going to be equal to, you can take alpha star is going to be equal to 0.05, and we're going to divide that by 3. And when we do that, our alpha star is going to be 0.0167. So the idea here is that you're adjusting alpha so it becomes much more difficult to reject the null hypotheses using these pairwise pieces. Okay, we want to keep the probability of making a type 1 error as small as possible is basically the idea. Okay, so the second thing that we're going to need from this is we're going to need the pooled standard deviation, and they gave that to us in the problem here below the table. So you see they gave us S pooled. Now the reason we're going to need that is because we're going to be doing 3 pairwise tests, and so we're going to have to get a pooled standard deviation, or an estimate of the pooled standard deviation among all of those. So we're a bit in lux because that's based upon the sample size. So to get that value that we want there, in other words, our pooled estimate of the standard error, what we got to do is we got to take the square root of sigma squared 1 divided by n1 plus sigma squared 2 divided by n2. Okay, so well, since the sigmas, that we're going to use the pooled value for that, okay, for each one of those, that's going to be 9.793. If we go back for a second and take a look, that's that value right there. Let me get us a fresh sheet of paper here so we're not scribbling all over that. Notice that's the pooled value, and the n's are going to be the same for each of them because n is equal to 14 for each of our groups. So we're nice. We set it up correctly that they're all the same. Okay, so all of those are equal to 14. So that's going to be 9.793 quantity squared divided by 14 plus 9.793 squared divided by 14, and that's going to be the same no matter which pairwise test you're working. So that's going to be approximately equal to, let's put squiggles here, right around 3.7. So we're going to run with that as being our standard error for each one of the tests. Okay, so that's going to be the denominator in our t-test statistic for every one of them. Okay, all right, so let's get after it. We got 3 of these that we need to do. So the first one, so we'll do treatment 1 versus say treatment 2. So T1 v T2, the smackdown between those two. So let's get whatever our t-test statistic. So it's our t-stat here. Our t-stat is the same old, same old. We're going to take the observed value So what we're going to do is take the differences between those two means for T1 and T2 and divide that by our pal right here, okay? All right, so how are we going to go get those? So let's go back for a moment. We need to actually go back and take a look at those means. Those were back up in 4.37. So, I mean, it would have been nice of them to have perhaps done us a proper and brought that table down into this problem. So we're going to need to take the treatment 1, which is 6.21, and subtract from that 2.86, okay? So let's see here, 6.21 minus, let's see, was it 2.86? I've got it on another screen to help me keep it straight in my head, okay? So 2.86, and we're going to divide that by 3.7, and it's going to give us back a test statistic of about 0.91. Okay, so we're going to go ahead and use the smaller of the 2 degrees of freedom, which is the conservative way of doing it. So in other words, our degrees of freedom here are going to be equal to 13, which is the 14 minus 1. Okay, and that's going to be the same across all of them. All right, so we want to know what is the corresponding p-value that is associated with that. Okay. So we're going to have a t distribution with degrees of freedom equal to 13, and we got our p-value is about 0.91. Okay, and then a negative 0.91 because we're saying they differ, so this is going to be a two-tail. And I can tell you already, without even doing anything, I can see that that's greater than 5% just based upon my drawing. But we can go ahead and actually get our calculator to do that for us too. Just go use the TCDF. Back here, where'd you go? There's my calculator. I've got to shut off my whiteboard first. Forgot about that. Okay, there's my calculator. So let's go ahead and clear that out. And we'll go second distribution. And I'm going to go down to TCDF. Remember, we use this just like we did normal CDF, but we only have to put in two things. We've got to put in our lower, which was what, 0.91, our upper, which is going to be E99. And we've got to put in our degrees of freedom, which in this case was equal to 13. We're going to paste that command, hit an enter, and then we're going to times that by 2 and double it. Doesn't matter, we don't really need to because it's already greater than 5%, and that's our corresponding p-value. So the main thing that we need to see here is that our p-value was big, okay? And given that our p-value was big, p-value is greater than 5%, so we failed to reject that those means are different from each other. Oh, scoop up, my bad. Oof. Excuse me, I got to correct something here. Let's get my eraser going here for just a second. Oh my, okay, well, all right, we'll use that. We'll scribble it out. Oh my gosh. Why am I getting so panicked here? Because I grabbed the wrong alpha. I need to use alpha star here, right? And so our alpha star that we discovered earlier was what? It was 0.0167, okay? There we go. Okay, so let me do one more of these pairwise ones for you, and I'll let you take the rest of them, okay? So let's go ahead and let's do T1 versus T3. So if we do T1 versus T3, then that's going to be 6.221. Again, I'm referencing, I've got the table open up on another screen here for me. You got to look at 5.37 to get these numbers, okay? Minus negative 3.21. Those are the means from that table. Both those divided by 3.7, which gives us a corresponding p-value of 2.55. T-value, I think I said p, but I meant to say t-value of 2.55. Okay, so that's our corresponding t-test statistic, okay? All right, so now we're going to go in and again using degrees of freedom equal to 13, we're going to go in and calculate our corresponding p-value. I'm going to run out a little bit of space here, but this will be all right. So 2.55, so we're going to go down here negative 2.55 and then positive 2.55. And the corresponding p-value is going to be these shaded regions right here. All right, so let's go get our calculator back out. Let's get a calculator out. We're going to go in and we're going to go second distributions. We'll go TCDF, which is option 6. Put in our lower bound was 2.55. Upper bound is E99. Degrees of freedom is 13. Paste that in, hit an enter. And then we're going to have to multiply that times 2. Okay, so that is going to be, again, bigger than the degrees of freedom. So you're again going to fail to reject, okay? So, hey now, come back here, you. So the corresponding p-value was, let's go ahead and get that number one more time, was 0.024. Okay, so again, we're going to end up failing to reject because notice we would have rejected at 5%, but we're not using 5% as our level of significance. We're using alpha star here, okay? So we again are going to fail to reject. I'll let you do the last one, see how that comes out for you. Again, if you have any questions, any of this, I know this is a little more cumbersome than some of the stuff that we've done earlier in this section, but it's basically review material, with a little bit of a twist to it, okay? So don't be shy about asking additional questions and post those in the Q&A form. Hopefully this gets you jump started.